There is a storm in our solar system that has been raging for more than 300 years. A storm so enormous that Earth, with its 12,742-kilometer diameter, could fit inside it. This is Great Red Spot on Jupiter, the largest and longest-lasting storm ever observed. First recorded in 1665 by astronomer Giovanni Cassini, this gigantic anticyclonic vortex has persisted for centuries in Jupiter's turbulent atmosphere. At its widest in the late 1800s, it stretched over 40,000 kilometers across, large enough to swallow nearly 3 Earths side by side. Today it measures about 16,000 kilometers in diameter, meaning Earth could still fit within it, but it has been steadily shrinking over the past 150 years. Wind speeds inside the storm reach up to 430 kilometers per hour, about 270 miles per hour, far exceeding the strongest hurricanes on Earth. Unlike storms on our planet, the Great Red Spot is not fueled by warm oceans or weakened by land. It floats within Jupiter's thick atmosphere, which is composed mainly of hydrogen and helium. The storm rotates counterclockwise and is classified as a high-pressure system, opposite of hurricanes on Earth. Observations from spacecraft such as Voyager 1, Galileo and Juno show that while the storm is shrinking and becoming more circular, it remains intensely powerful. A storm bigger than Earth. The Great Red Spot is a gigantic high-pressure anticyclonic storm located in Jupiter's southern hemisphere, centered around 22 degrees south latitude. At its widest in the late 1800s, it measured more than 40,000 kilometers across, large enough to swallow 3 Earths side by side, given Earth's diameter of about 12,742 kilometers. Over the past 150 years, it has steadily shrunk, and today it spans roughly 16,000 kilometers, about 1.3 times the width of Earth, meaning our entire planet could still fit comfortably inside it. Wind speeds within the storm reach up to 430 kilometers per hour, around 270 miles per hour, far exceeding the strongest hurricanes ever recorded on Earth. Unlike terrestrial hurricanes, which are fueled by warm ocean water and typically last days or weeks, Jupiter's Great Red Spot has persisted for at least 350 years, first documented in the 17th century. Because Jupiter is a gas giant composed primarily of hydrogen and helium, there is no solid surface to disrupt or weaken the storm. Its immense longevity and scale challenge traditional models of atmospheric dynamics, making it one of the most extraordinary and enduring weather systems ever. It has been raging for centuries. Astronomers first observed the Great Red Spot in the 1600s, possibly as early as 1665. That means it has been active for at least 350 years, and maybe longer. On Earth, storms lose energy when they hit land or cooler water, but on Jupiter, there is no solid surface in the traditional sense. It's a gas giant composed mostly of hydrogen and helium. There is nothing to slow the storm down the way friction weakens storms on Earth. Winds faster than any hurricane. Wind speeds inside the Great Red Spot reach up to 430 to 680 kilometers per hour, about 270 to 425 miles per hour, depending on measurements. That's far stronger than the most powerful hurricanes ever recorded on Earth. The storm rotates counterclockwise, marking it as a massive anticyclone. The energy driving it comes from Jupiter's intense internal heat and rapid rotation. Jupiter spins once every 10 hours. Jupiter is a planet of layers and chaos. Jupiter does not have a solid surface like Earth. Instead, as you descend through its thick atmosphere, pressure and temperature rise dramatically. The planet is composed primarily of hydrogen and helium, and deeper inside, under pressures millions of times stronger than Earth's atmospheric pressure, hydrogen is compressed into an exotic state known as liquid metallic hydrogen, a phase that conducts electricity and helps generate Jupiter's immense magnetic field, which is about 20,000 times stronger than Earth's. The Great Red Spot floats within Jupiter's upper cloud layers, which are made mainly of ammonia ice crystals, along with compounds like ammonium hydrosulfide and water deeper below. Beneath those colorful cloud bands lie thousands of kilometers of turbulent, churning atmosphere with no clear boundary between sky and surface. The storm is not only enormous in width, currently about 16,000 kilometers across, but also surprisingly deep. Data from Juno, which has been orbiting Jupiter since 2016, indicates that the Great Red Spot extends roughly 300 to 500 kilometers below the visible cloud tops. That depth is far greater than most storms on Earth, which typically extend about 10 to 15 kilometers into the atmosphere. The Great Red Spot is not a shallow surface feature. It is a vast, vertically structured vortex embedded within one of the most extreme atmospheric environments in the solar system. Why is it red? The exact reason for the Great Red Spot's reddish color remains an active area of research, but scientists believe it results from complex chemical reactions in Jupiter's upper atmosphere. The planet's clouds are primarily composed of ammonia ice, with deeper layers containing ammonium hydrosulfide and water vapor. Laboratory experiments and spacecraft data suggest that ultraviolet sunlight from the sun interacts with ammonia and trace amounts of sulfur compounds, or possibly phosphorus and carbon-based molecules, producing reddish chromophores, chemicals that give the storm its distinctive hue. Observations from missions such as Voyager 1, Galileo, the Hubble Space Telescope, and Juno have shown that the storm's color is not constant. Over decades, it has shifted from deep brick red to paler orange and even salmon tones, sometimes becoming darker as it shrinks in size. These variations suggest ongoing changes in altitude, cloud composition, and chemical processes within the vortex. Wind speeds inside the storm can exceed 430 kilometers per hour, continuously mixing atmospheric gases and influencing the chemistry at different levels. The evolving color of the Great Red Spot is more than a visual feature. It is evidence of dynamic atmospheric reactions occurring in a hydrogen-helium world, where sunlight, pressure, and exotic chemistry combine in ways scientists are still working to fully understand. It's shrinking. Over the past 150 years, astronomers have carefully tracked the changing size of Great Red Spot on Jupiter and found clear evidence that it is shrinking. In the late 1800s, measurements estimated its length at more than 40,000 kilometers across, wide enough to fit nearly 3 Earths side by side. Today, it measures closer to 16,000 kilometers in diameter, roughly 1.3 times the width of Earth. Along with shrinking, the storm's shape has changed. It was once more oval and elongated, but it has become increasingly circular as it contracts. Despite this reduction in size, the storm has not simply weakened. Observations from the Hubble Space Telescope and Juno indicate that wind speeds within the outer regions of the vortex have increased in recent years, in some areas exceeding 430 kilometers per hour. This suggests that the storm may be intensifying in certain layers, even as its overall footprint decreases. Scientists are still debating whether the Great Red Spot is slowly dissipating after centuries of activity or undergoing a structural transformation driven by changes in Jupiter's atmospheric jet streams and energy flows. Rather than fading quietly, the data indicate it may be evolving into a new phase of its long, Jupiter's powerful jet streams. Jupiter's atmosphere is organized into vivid, alternating light and dark bands, known as zones and belts, created by powerful jet streams that race around the planet at speeds exceeding 500 kilometers per hour. These jet streams flow in opposite directions, forming sharp boundaries of shear that shape Jupiter's turbulent weather systems. The Great Red Spot is located around 22 degrees south latitude, positioned precisely between two major jet streams, one moving eastward and the other westward. These opposing flows act like atmospheric guardrails, confining the storm and preventing it from drifting significantly north or south. Because Jupiter lacks a solid surface, there is no land to disrupt or weaken the vortex, allowing it to persist for centuries. Observations from spacecraft and telescopes show that smaller storms and vortices are frequently drawn into the Great Red Spot, where they merge and transfer energy into the larger system. In some cases, these mergers temporarily intensify the storm's winds or alter its shape. Rather than existing in isolation, the Great Red Spot is embedded within a constantly shifting network of jet streams, eddies, and turbulence. Its longevity appears to depend on this dynamic balance, stabilized by surrounding jets and occasionally energized by absorbing neighboring storms, making it not just a survivor, but an active participant in Jupiter's vast atmospheric engine. A planet that radiates more heat than it receives. Jupiter emits significantly more heat than it receives from the Sun, radiating roughly 1.6 times the energy it absorbs. This excess energy comes primarily from residual heat left over from the planet's formation about 4.5 billion years ago, along with ongoing slow gravitational contraction through a process known as Kelvin-Helmholtz contraction. As Jupiter very gradually shrinks, by only a few centimeters per year, gravitational potential energy is converted into thermal energy, heating the planet's interior. This internal heat rises upward and helps drive the powerful convection currents that shape Jupiter's turbulent atmosphere. Unlike Earth, where weather systems are powered mainly by uneven solar heating of oceans and land, Jupiter's storms are fueled from below as well as above. Combined with its rapid rotation period of just under 10 hours, the fastest of any planet in the solar system, this internal energy generates strong Coriolis forces that organize the atmosphere into jet streams, bands, and massive vortices. The Great Red Spot is sustained in part by this deep energy reservoir, allowing it to persist for centuries in a way no terrestrial storm could. Jupiter's weather is not simply sunlight-driven. It is powered by the planet's own internal heat engine, making its storms fundamentally different from those on Earth. Juno's close-up revelations. Juno, which has been orbiting Jupiter since July 2016, has delivered the most detailed measurements ever taken of the Great Red Spot. By using its gravity science instruments during close flybys, Juno detected subtle variations in Jupiter's gravitational field caused by mass differences beneath the storm. These measurements revealed that the Great Red Spot extends approximately 300 to 500 kilometers below the visible cloud tops. While that depth is small compared to Jupiter's enormous radius of about 69,911 kilometers, it is immense when compared to storms on Earth, which typically extend only 10 to 15 kilometers vertically. Juno's microwave radiometer has also allowed scientists to peer beneath the upper ammonia cloud layers, uncovering complex internal structures and temperature variations within the vortex. The data suggests the storm is deeply rooted, but not connected to the planet's metallic hydrogen interior, meaning it is a powerful yet relatively shallow atmospheric phenomenon. By combining gravity data, microwave observations, and high-resolution imaging, Juno has helped scientists better understand how energy circulates within the storm and how interactions with surrounding jet streams allow it to persist for centuries. These findings have transformed the Great Red Spot from a visible curiosity into a measurable, three-dimensional atmospheric system shaped by Jupiter's immense internal heat and rapid rotation. Will it ever end? No one knows exactly when or if Jupiter's Great Red Spot will disappear. Most storms in the solar system are short-lived by comparison, yet this vortex has persisted for at least 350 years, first recorded in the 17th century and possibly even earlier. Although it has been shrinking steadily since the late 1800s, decreasing from over 40,000 kilometers across to about 16,000 kilometers today, it remains powerful, with wind speeds exceeding 430 kilometers per hour. On Earth, even the strongest hurricanes fade within days or weeks, but Jupiter's lack of a solid surface means there is no land to disrupt or weaken such storms. Instead, the Great Red Spot is stabilized by surrounding jet streams and occasionally energized by absorbing smaller vortices. Some scientists suggest it may continue contracting until it dissipates entirely, while others propose it could reach a stable equilibrium at a smaller size and persist for centuries more. Jupiter itself is a dynamic world, radiating about 1.6 times more energy than it receives from the Sun and rotating once every 10 hours, driving immense atmospheric forces. The Great Red Spot stands as a reminder that planetary weather can operate on scales of a storm larger than Earth, older than modern meteorology, and powered by a planet that radiates about 1.6 times more energy than it receives from the Sun. Jupiter's Great Red Spot is far more than a swirling patch of color. First recorded in the 1600s and still raging today, this anticyclonic vortex currently spans about 16,000 kilometers across, wide enough to engulf our 12,742-kilometer wide planet. Wind speeds inside the storm can exceed 430 kilometers per hour, and data from Juno show it extends roughly 300 to 500 kilometers deep into Jupiter's atmosphere. Unlike hurricanes on Earth, which depend on warm oceans and fade within days, this storm is sustained by Jupiter's internal heat, rapid 10-hour rotation, and stabilizing jet streams that act like atmospheric boundaries. Even after shrinking from more than 40,000 kilometers in the 19th century, it remains one of the most extreme weather systems ever observed. Jupiter's Great Red Spot is a vivid reminder that the universe operates on scales of size, energy, and time that challenge human intuition. Beyond our world, storms can last centuries, span continents, and draw power from the deep interiors of giant planets. Proof that planetary weather does not simply pass,